SwayamPrabha. Digital India. Educated India.
Welcome back. In lecture 33, we will talk about sewage systems, and this is the part 1. So, we will cover different concepts in this lecture. These are we will first discuss about sewage systems, then we will talk about on-site sanitation systems, and within on-site sanitation systems, we will talk about pour flush water seal latrine, we will talk about leach pits, septic tanks, and secondary treatment and disposal of effluents. So, when we are designing or choosing a particular kind of sewage system for an urban area, it depends on many factors, or it could be also for a small community as well. And usually ULBs or the other or whatever agency is actually developing this kind of networks, they should reserve space for in an urban area for sewer lines, sewage pumping stations, sewage treatment plants, because even though not everything will come together, but this we have to reserve these spaces at the beginning itself. Otherwise, in future there will be it would be very difficult to acquire this kind of spaces. So, once people know about this kind of infrastructure or spaces reserved for infrastructure, they are also confident about buying houses, or developers are confident about building their apartments over there. So, it helps in both ways, right. So, when we talk about sewage systems, there are different kind of systems of course, but primarily there is the conservancy system and the water carriage system. So, we have broadly touched upon that in our earlier lecture, where conservancy system is the old system where manual scavenging is involved. That means you need to clean the system, and by human agency, it is not automatic system and so on. Whereas water carriage system is an automatic system, that means from toilets are directly connected with pipe network, where water is used to drain all the waste, all the sewage into the pipelines, and then eventually it is transported to the treatment units where it is treated and then disposed of. So, in between this conservancy system and water carriage system, there is also on-site sanitation system and decentralized sanitation system. So, on-site sanitation systems could be called by a different, it could be different from a conservancy system, but there are certain overlaps. That means, some of the toilets used in on-site sanitation systems could be called as a conservancy system, like a pit toilet, right. Whereas, other toilets like more advanced kind of septic toilets and a septic tank, and then other kind of effluent treatment systems that we can design in on-site sanitation system, they may not be part of the conservancy system. So, the other one is the decentralized sanitation system. Again, there may be overlaps between on-site sanitation systems and water carriage systems in this decentralized sanitation system. That means, some of the systems could be it's similar to a water carriage system, some of the system even though similar may be different. So, that is why we can have these 4 kinds of system distinctly discussed separately. So, what is the conservancy system? So, usually in conservancy system, we have this conservancy latrines, and where the human excreta is removed using human agency, and the removed sludge is buried in trenches for conversion to manure after 2 to 3 years. For this, we need to have also land for that as well. So, sewage and stormwater in this particular system is conveyed through closed or open drains and disposed in water bodies without treatment. And sewage is sometimes could be used for gardening and farming, and stormwater is separated from maybe sewage, and maybe in case we have got pipelines or cover, we are taking stormwater through pipelines, then the requirement or sewers that is required for that would be of smaller size. And usually one big thing of conservancy system is latrines have to be separate from buildings in most of the cases, right. In some cases, or in certain kind of toilets cannot be within the building itself, and it has got low aesthetics, and there may be odor involved in this kind of systems, and liquid refuse could penetrate into subsoil and subsequently go to groundwater, because we are disposing the waste directly into the soil, and decomposition of sewage causes insanitary conditions. So, you have a broad idea about the conservancy system. That means, we have got these toilets where the waste is actually disposed of in maybe pits and all, or holes in the ground, and it has to be cleaned via human agency, and then there is no way of cleaning it via mechanical means in that particular case, and then there is not much consideration about sullage or the stormwater as well. So, on-site sanitation systems, these systems are suitable for unsewered areas where population density is not adequate, and it sometimes we can have a decentralized system also in this unsewered low population areas, but we have to look into both the options, and then we have to decide. And the treatment of sewage is on site, that means we are treating it locally, and but septage treatment that is off site. So, you have, this is the difference with the conservancy system. So, we are having sewage treatment via septic tanks or via twin pits on site, but the septage part, when we are removing the sludge and all from this particular septic tank and all, then this septage that is coming out of the septic tank, this has to be properly treated, maybe off site in maybe a treatment plant, maybe a dedicated treatment plant, maybe in the existing sewage treatment plant, and so on. So, this include both basic systems like pit latrine, septic tank, soak pit, and also advanced facilities like the Jocasso. So, these are the different kind of toilets that are also, or latrines that are also present in on-site sanitation systems. So, let us look at the first kind of toilet or latrine, that is called the pour flush water seal latrine. So, that means you pour water to flush it, and this is also having a water seal. That means the squirting pan will have a sort of a water seal in that, so that the gases or insects and all cannot come back from the pit inside that particular squirting pan. So, usually this kind of toilets are cleaned by pouring about 1.5 to 2 liters of water, and we have a leaching pit. This is a pit in the ground. A leaching pit is one which allows water to leach over from the sides. So, leaching pit is there and a squirting pan placed over it, and the size of the pit is around 1.3 meter to 1 meter, and it could be of depth of 1.5 meter to 2 meter depth, and so on. A vent pipe is connected over here, so that gases can pass, otherwise it will come back into the if there is no water seal and all, then it may come back, or it may sometimes leak as well. When pit is filled, it is covered by earth or ash of 60 centimeter thick layer, and then new pit is excavated. So, the entire structure has to be taken and placed over another pit, and this pit is covered by earth and ash of 60 centimeter or 2 feet thick layer. If liner is applied, odor reduces, and after 1 or 2 years the digested excreta is used as manure. So, because we are now using another pit, this after 1 or 2 years this becomes manure, and we can use the the sludge over there, and that could be for as a manure. So, a modified pit privy, this is a much better system, where the leach pit is kept away from the pan. That means, we have this toilet superstructure along with the squirting pan over here, and the pit is separate. And what is the benefit of that? That means, the toilet doesn't needs to be shifted. So, it remains where it is. Only thing is, this connection needs to be shifted to another pit. So, this is the design of the pit. It is a single pit system. The problem is its dislodging is difficult and unsafe due to undigested sludge. So, that means, if there is only one pit, it has to be cleaned at certain intervals. So, you are not able to stop using it, right. So, once the sludge, even if some part of the sludge is undigested, it has to be removed. So, it is not a good option. Mechanical dislodging is the only option, because human agency cannot do this. So, but many places mechanical agency is not there. And the other one is the double or twin pit system, where there are two pits and excreta is diverted to the second pit when the first pit is full, and filled pit is cleaned after 1.5 to 2 years when it has turned into manure. So, in this way we can avoid this problem, and two pits can be used continuously, and water seal prevents odor and insects, thus can be integrated inside buildings as well. So, it is better not to have pit trellis inside a building, but if required we can also have it because we have the water seal in place. Now, squatting pan with the only difference is because we are using a very little quantity of water, it is a pour flush system, there is no flushing cistern. So, that is why this squatting plan we use a different kind of pan design, where it is of a greater slope, 25 to 28 degree slope is given over here, and then which ensures flushing with little water, and the trap is having only a 20 mm water seal set on the cement concrete floor. So, this is the difference with standard pans, and you can see in this design the design of the bend and also the design of the trap, and as well as the design of this particular pan. So, this pit design that we were talking about, that means it is basically a leach pit or a leaching pit. Now, what it means is it allows leaching of water from its from the surface of that particular pit, and as you can understand that it is meant for both storage and digestion of excreted solids and infiltration of the waste liquids into the surrounding soil. So, the digested solids are actually stored inside. So, it has to have space for storage of the digested solid this excreta, and then the other part is the storage of the water and its eventual infiltration into the surrounding through the surrounding surface of that particular pit. So, when we design a leach pit, we have to first understand what is the sludge accumulation rate, because this will give me the space required to determine for how much sludge would be accumulated per person per year even. So, this is used to calculate the pit volume or the size of the pit, and water table level, age, water and excreta loading rates, microbial condition, temperature, soil and cleaning media. Cleaning media means if water is used for cleaning after or paper is used for cleaning. These are the two things that we need to consider when we design a particular pit, and usually when you determine the sludge accumulation rate, this is important, and particularly there are two kinds of pit, wet pit and dry pit. Wet pit is when the groundwater table is above the bottom of the pit, and dry pit is groundwater table below the bottom of the pit. So, that means that is why it is called a dry pit, and because the groundwater table is above, that means the infiltration rate would be lower, and that is why we require a higher volume in this particular case. Now, you can see in this particular table, this is the sludge accumulation rates is given for if you use water or paper, or if it is under dry condition or if it is under wet condition. Then if it is under wet condition, if the period between dislodging is 2 years or 3 years, then we see that the sludge accumulation rate is 0.04 meter cube per capita per year for water under dry conditions. For when paper is used for cleaning, then 0.053, which is a little bit higher, right, because of use of paper. And when we have wet condition, definitely 0.04 becomes 0.095. You can see the volume has almost doubled, and then that is for 2 year period. For 3 year period, it will be a little bit different. And then for soft paper, again you can see the values. So, basically when we determine the size of the pit based on the number of users, we can determine that per capita per year rate is given. From that we can determine the size or the volume that we have to reserve for sludge storage, right, or you can say digested excreta storage, right. Then we have to understand that once the accumulation volume is understood, suppose we have got a pit. So, this is the accumulation volume, the first part. Then the other part is the infiltration. We have to understand that how much of water will be coming here, so that it will infiltrate from the surrounding walls. It cannot go below because we have got sludge here. So, it will only infiltrate from the side walls. So, long term infiltration rate of the liquid fraction across the pit soil interface depends on soil type, since pores gets clogged. So, there are different kinds of soil, each has got different sizes of pores, and that determines what would be the infiltration rate for this particular soil type. So, for example, when we look into sand, the infiltration rate is 50 liters per square meter per day. Then sandy loam, it is 30 liters per square meter per day. Porous silty loams, porous silty clay loams 20 liters per square meter per day, and when it is compact silty loam and clay type of soil, it is very little, which is 10 liters per square meter per day. Actually, when it is 10 liters, it is not feasible to have a leaching pit over there. So, this is the infiltration rate, or it is very difficult to have a infiltration rate over this kind of a pit toilet over there. So, the next thing that we measure is what is the hydraulic loading on the pit, that means how much water gets inside the pit. We assume that it is about 9.5 liters per day per person. So, you can if based on the number of persons who is using the pit, you can understand how many liters of water goes into that pit, and we the perimeter from and based on that volume of water divided by the infiltration rate, actually we understand how much surface area is required for the water to infiltrate into the surrounding soil. So, if I have a leach pit and water is being infiltrated, so I will like to understand what kind of surface area is required for this, because water would be going from the surrounding walls, right. So, the perimeter from the pit bottom to the invert level of the pipe is considered for infiltration. So, this is the invert level of the pipe, that is the pipe that is coming from the toilet, from the latrine, and this is the invert level of that pipe. So, from this and until this is that the pit bottom, how that of course leaving the accumulation, the zone where the sludge is accumulated. So, that part is determines the kind of depth that we require. So, pit bottom is not considered because it will clog. So, infiltration rate is total flow in the pit per day divided by infiltration rate, infiltration area requirement. So, based on that we calculate the surface area that is required for this particular pit. And then minimum period of effective pathogen destruction is 1.5 years. So, that is after that time period we will be cleaning or shifting to a new pit, and once we shift to a new pit we will leave it for 1.5 years, so that the sludge gets digested and all the pathogens are destroyed, and the optimum pit emptying frequency is around 1.5 to 3 years. So, these are typical designs of leach pit toilets, and typical sizes of leach pits are also given in this particular table, and depth from bottom of the pit to invert level of incoming pipe, that is over here, and this is the diameter of the pit. For dry pits and wet pit it is given. So, for 5 users, 10 users and 15 users you can have this figure. So, that means for 10 users a dry pit requires around 1100 diameter and 1300 depth, right. So, this is in millimeters of course, and then when we design the pit, over here you can see this is the ground level, this is the pit, this is the lining to the pit, this is the water, this is the invert level of that particular pipe that is coming in, and then this is solid brickwork in cement mortar, the top part. Over here infiltration does not happen, so because the infiltration starts below this particular level, and over here it is brickwork in cement mortar with honeycombing in alternate brick courses up to invert level of pipe or drain. So, that means honeycombing means when we have the bricks laid like this, that means the structure is there, but we have also empty spaces through which water can infiltrate into the soil. So, in this way we create the lining of the pit and water will infiltrate, and this is the base of the pit. So, pit is raised by 300 mm. Over here it is more or less flat, but we can raise it a bit higher. This is to ensure that in case of any kind of waterlogging or flooding, this pit is not filled with water from the top. And then in infiltration rate, we have already discussed. For black soil, it is 10 liters per meter square per day. For rock strata, it is 20 liters per meter square per day. And we should also design the pits far away from the drinking water sources. Otherwise, there may be chances of contamination. So, over here it is a twin pit system. You can see one toilet connecting to two pits, outlet to be opened alternatively whenever a particular pit is used. And after this pit is used, then we clean the pit and again we can use it. So, we use a pit for 2 years and so, and then we go to the other pit after cleaning it. Then we come to septic tanks. You are all aware of septic tanks. Maybe you have studied it in earlier classes. And over here, we have seen that in septic tanks, it combines both the two processes. One is sedimentation as well as digestion of that particular excreta. So, this is the standard design of septic tanks. And as you can see, this is the section. So, this is where the pipe comes in. And this is the first chamber and this is the second chamber. So, in the first chamber there is a baffle wall. So, the sewage goes below, and then there is a slope also given over here, and over here there is an opening at the top. So, sedimentation happens over here, and after that the effluent goes from the top and then goes to the next chamber. Some amount of sedimentation also happens over here. Then it travels like this, and then there is the outlet, right. So, this is the standard design of a septic tank. This is a 2-chamber septic tank, right. There could be even more chambers than this. So, the detention period of water in the septic tank is 1 to 2 days, but in other cases we have seen even less than 1 day of detention has been also designed in some cases, but roughly in most cases it is 1 to 2 days. That means, the water that comes in, the design of the tank is such that it would be holding the accumulated sludge, plus there is a zone for sedimentation, plus the space required for water to be stored for detained for 1 to 2 days. So, suspended solids settle down, which is the sludge, and they form the sludge, and aerobic digestion of sludge takes place, anaerobic digestion, because there is no oxygen, and organic matter is reduced and gases are released. So, carbon dioxide, methane and hydrogen sulfide gases are released. So, sometimes we will have a vent pipe over here as well from the septic tank, and then effluent contains both dissolved and suspended impurities and pathogens, and so we cannot dispose it directly into open drains and or to the sewer network. So, it has to be disposed through lined channels, or it should be treated further, and suitable for individual homes and small communities up to 300 persons. So, this is more or less the basics of a septic tank, and it could be single or twin compartment. In this we can see a twin compartment design, or it could be a single compartment design as well. Sometimes we can have, by placing of baffles we can create further compartments, and first is twice the size of the second. The first chamber is twice the size of the second, and the liquid depth is 1 to 2 meters, and length is to breadth is either 2 or 2:1 or 3:1. So, this is the proportion. So, these are some of the typical sizes of septic tanks for 5 users, 10 users, 20, 100, 300 users. You can see that for 20 users the length is 2.3, breadth is 1.1, and this after 2 years the liquid depth, if cleaning interval is 2 years, is 1.3 meters, or if it is 3 years, then the liquid depth is 1.8 meters. So, this difference of 0.5 meter is because of excess sludge accumulation for that 1 year period. All right. So, that is how we will design a septic tank. So, whenever we are designing this septic tank, we need to think about how do we dispose of this particular effluent, and usually we dispose this effluent through land disposal. We can also treat it, of course, but when we dispose it in the land, we need to consider about the water table of that area, the climate of that area, vegetation, concentration of suspended solids in the effluent. So, these are the things we need to consider, but basically we dispose this particular effluent through soil, like in a normal pit toilet, we allow the water to infiltrate. Similarly, over here also we allow the effluent to infiltrate into the ground, but for that we will design soak pits or dispersion trenches. So, we cannot just let it on the surface of the ground. So, we need to actually put it inside a soak pit or a dispersion trenches. So, soak pits are more or less similar to like the pit toilets, the pits in the pit toilets, but only thing is it only the solid or excreta part is that it is already taken care of, because it is already being digested in the septic tank after sedimentation. So, only the clearer effluent comes in. So, it has got impurities, it has got pathogens, but relatively less quantity. So, soak pits and dispersion trenches are designed where percolation rate is below 25 minutes per centimeter. So, this is something which is important. If it is more than that, that means it takes water to percolate even higher, then we do not design it. So, what is percolation rate? Percolation rate is determined by excavating a hole to a depth of the trench and measuring fall in level of water by 1 centimeter and then measuring the time taken. So, a test hole diameter can be 10 to 30 centimeter, and other empirical formulas also exist. For other empirical formulas also exist, I will come down to that formula later on. But basically, we allow water to infiltrate, and we see that when 1 centimeter of level of water comes down, we can understand what is the time taken for that, and that is the standard percolation rate for soil in minutes. So, depth of water table has to be 2 meter or more, then only we can go for this soak pits and dispersion trenches. Otherwise, if the water table is pretty high, then water will not infiltrate inside, or it will actually mix with the groundwater. So, how do I decide on the size of the soak pits and dispersion trenches? So, the first thing that we need to determine is the subsurface soil area required for soak pits or dispersion trenches. So, this is could be determined using the formula Q is equal to 130 root T, right. So, Q is the maximum rate of effluent application in liter per day per meter square of leaching surface. So, if I can determine the amount of water or the effluent that I can maximum rate of effluent application, then from that itself we can determine the total area required for this particular trench, and T is the standard percolation rate for soil in minutes. So, that we just discussed. So, this is one formula Q equal to 130 root T, but we can always have other empirical formulas, which also there are other formulas also there which could be used, but this is the one which is commonly used. So, one thing we should be careful is for dispersion trenches, we only consider the area of the trench bottom. That means, in dispersion trenches you will see that the pipeline is like that. We have got this is a trench that we dig in the ground. We have got gravel and all this inside. So, the water goes only through below. The infiltration happens below. Whereas, in case of soak pits, the effective sidewall area below the inlet level is only considered. Similar to a standard pit toilet, it is similar principle. So, we only assume that water goes from the sidewalls. So, this is the soak pit design. Soak pits can be lined or unlined. So, over here you can see a lined soak pit. So, 30 centimeter thick sand casting. So, this is sand, and the top part is brick chamber with dry joints, and this is aggregate inside. So, this is the inlet of the effluent, this is the ground level, this is raised so that it could be covered. So, it is raised so that it does not gets flooded in case of there is inundation over in this particular area. So, effluent comes in, it comes to this box that is created, again it is created with brick just to create a sort of chamber. From there it goes into the surroundings and it goes via the media inside. The media actually can treat this water further, because there is biological aerobic digestion takes place over here, because on the surface of this particular media there are some amount of bacteria which actually helps in this digestion, and then it passes through the side walls into the surrounding soil. So, this is how a soak pit operates, and usually it is filled with rubble or brick bats for unlined ones, and then the shape it could be circular or square, and dimension is 1 meter across, depth is 1 meter below the inlet pipe. So, this is something around 1 meter, and covered and raised above ground to prevent flooding. So, this is the design of a soak pit. Similarly, this is the design of a dispersion trench. As you can see, this is the ground level, this is ordinary soil, that the top part, and over here you can see that this is crushed stone below, and this is coarse aggregate, and this is a 75 to 100 mm earthenware pipe through which the effluent is being actually passed through. From here, it's a earthenware pipe with open joints, so the effluent leaks out to the surroundings, and it actually gets down through the bottom of this particular trench. Maybe some amount happens from the sides, but it is insignificant. Most of we assume that the trench actually is infiltrating only from the lower surface, this bottom surface. So, in case of dispersion trenches, usually these are 0.5 to 1 meter deep, and then 0.3 to 1 meter wide with gradient of around 25%, 0.25% actually, sorry, not 25%, 0.25%. So, it's very minimum gradient slope is given. It contains open jointed earthenware or concrete pipes 80 to 100 millimeter in size or 75 to 100 millimeter in size. A bedding of 15 to 25 centimeter of washed gravel of crushed stone, this is that bedding, and covered by coarse gravel and crushed stone up to minimum 15 centimeter, and next excavated earth mound at top to prevent flooding. So, it is raised a bit to prevent flooding. Effluent is distributed via distribution box and trenches radiate outwards. So, this is the section of the trench, of course, but the overall design is like this, where this is the inspection box and this is a baffle wall. The effluent is put into this box first, and from there are 3 directions. It could be only one dispersion trench as well, but here we can see 3 dispersion trenches going in 3 directions, and there is some gap in between these 2 arms, and as you can see that each dispersion trench maximum can be of 30 meter in length, and minimum spacing in between them should be 2 meters, right. So, beyond 30 meters it becomes ineffective, and the same formula is used, Q equal to 130 root T, that we have already learned. So, you can see that 1.8 to 2 meters is the gap in between this particular dispersion trenches, and the design is this section is basically this section that we can see over here. Now, let us look at a small problem to design the size of a dispersion trench. So, design a dispersion trench for disposal of septic tank effluent for a population of 100 with sewage flow rate of 135 LPCD, and take the percolation rate T equal to 3 minutes. So, we have got sewage flow rate of 135 LPCD and a population size of 100. Now, dispersion trench may be adopted in areas where percolation rate is not exceeding 60 minutes. So, that means compared to the soak pits, this allows a little bit more. Minimum absorption area or actually it is not exceeding 60 minutes. That means, if it is beyond 60 minutes, we cannot actually use it, and minimum absorption area of trenches can be calculated based on Q equal to 130 root T that we have discussed. And let us directly go into the problem. So, total sewage is 135 liters per capita per day multiplied by 100, which is 13,500 liters per day. So, Q equal to 130 root T comes to 130 into root 3 because T is equal to 3 minutes, and then we get it around 225.17 liters per meter square per day. So, this is the amount of maximum amount of infiltration that can happen. So, this is the application rate of sewage, we can also say. So, if I divide the overall value with this one, then total we can get the area, total area or the surface area through which dispersion can take place. So, total sewage divided by Q is the area of the trenches that is required. So, the bottom area of the trench that is required. So, when we calculate that, we get around 59.95 meters square. So, we take the maximum width of the trench as 1 meter, as discussed that maximum 0.3 to 1 meter is the width of the trench, and length is equal to, so if I have a 1 meter wide trench, so of course we have got almost 59.95 meters of length of this particular trench. So, but we have also discussed that length cannot exceed 30 meter. Thus, we just divided into 2 trenches and each length is 30 meters. So, that means in this particular design we will have a inspection box. From there we can have 2 trenches of 30 meter and then each trench is of 1 meter wide. So, this is the design of the dispersion trench for this particular problem. So, to conclude, on-site decentralized and conventional sewerage system has to be chosen as per the context. Effluent from septic tank is harmful for human health and care should be taken that it is disposed properly. These are the references. Thank you.